Now I'd like to share 7 popular UML diagrams with you. So we're going to take a look at the 7 most used, most popular UML diagrams, the diagrams that most architects would use. And we're going to take a closer look at what the diagram looks like, what the different symbols in the diagram mean exactly, and what the capabilities of that particular diagram are. So let's dive right into it. So let's start out with the component diagram. Now, as you can imagine from the name, the component diagram describes components in your architecture. Now, components are modular software building blocks that you can use to assemble software applications kind of like Lego. So every component is a Lego brick, and you basically just create your architecture by assembling these bricks in different configurations. So the component diagram shows components. I'm going to try something new. I'm going to use a laser pointer. So take a look at this. So here, this is a component in the component diagram. And the component has an interface. So this bit here, I'll get back to that in a second, but this is a public interface. So this component is connected to this component. So this whole thing here is one big component. And it's a nested component because it has this internal component, and here is another internal component. So the interesting bits of this component diagram are the fact that components can be nested. So that's interesting. You can create hierarchies of components. That also means you can create a component diagram on a super high level and then create that in the first iteration and then drill down by going inside those components and mapping out their internal structure. Now here is the interface, and the interface, you draw it like this. So a public interface is drawn like a stick that comes out of a component, and then this cup means that this is the specific interface type that this component expects. So it's an input, and the component expects the input to be of a particular type. Now another component will look like this. It will also have a stick, and it will have a ball on the top. And the ball is a specific type, a specific data type that this component provides. So when the expected type and the provided type are the same, then the components are compatible and their interface connectors can join. So we have a notation that specifies a type and a directionality of data communication. So the providing component provides data, and the expecting component receives the data. So the data flows in a particular direction, and it has a specific type. So the component diagram shows components, obviously, but it also shows the implemented and required interfaces for each component. So this allows you to create a fairly detailed representation of your architecture. If you choose to implement your entire architecture as components, then with the component diagram, you can map out all existing components, you can describe all public interfaces of the components, and you can describe how each component calls another component. That's a fairly complete description of a system. Next up is the class diagram. The class diagram shows classes in your architecture. So I'll use the laser pointer again. So here is a class called order. Here's a class called customer. And here is a class called express order. Now you can see there are a number of symbols used in this diagram. For example, this arrow here, let me copy it up here. So it's an arrow like that, and it has 2 characters. Now on this side is an asterisk, and on this side is a 1. Now these symbols represent cardinality. So this means that a customer can have 0 or more orders. So the order class has a reference to the customer class, and it has cardinality of 0 or more. So that's a lot of information that becomes apparent from this diagram. Now, between the express order and the order is another arrow. Let me copy it here. It looks like this. This arrow denotes inheritance. So this says that express order is derived from order. Express order is a special case of an order. And finally, look at the contents of the classes. Right here, you can see there are 3 fields listed: date, prepaid, and price. Date is a date, prepaid is a boolean, and price is a decimal. Here we have name and address, both strings. And here we have a field called markup, which is a decimal. You can see that behind each type is again a cardinality. So 1 means the field is mandatory, and 0 to 1 right here means that the field is optional. It can contain null. So again, that's a lot of information that we can derive from this diagram. The diagram not only accurately describes the classes, whoops, let me use a pen for that. It not only accurately describes classes, it also describes all public methods and fields. And if that's not enough, it also describes all associations between classes, all generalizations, and it describes cardinality. So that's a lot of information packed into a fairly simple visual diagram. Okay, next up, the sequence diagram. The sequence diagram is used when you have a complex call sequence between 2 or more objects, and you want to draw in what sequence these calls are made. So the sequence diagram contains the classes up here. So we have 3 classes. We have order, we have order line, and we have product. The class making the call is order. So this bar here means that the order class is initiating the call. So the first thing that happens is that the order class calls getQuantity on the order line class. Oops, sorry about that. So the order class calls getQuantity on the order line class. The getQuantity call returns an integer. Then the order class calls getProduct on order line, which returns a project object. And finally, order calls getPrice on the product object, the product class, and this returns a decimal value. And if that wasn't enough, look at this here. It's a loop. So this entire section, everything in this square box, is looped. So this call sequence is repeated for every order line in the order. So what do we see? The sequence diagram shows a call sequence. It shows the calling class. It shows the called method and the return data type, and it can depict loops. So again, a lot of information for a simple visual diagram. Next up, the state diagram. So state diagrams are used to describe the discrete states of a state machine and all valid state transitions. So in the example here, I've created a simple state machine that handles a calculator, like a pocket calculator, and you press the buttons. Every button press is an event for the state machine, which puts the machine in a different state. And well, let's take a look. So first of all, you start here at the start symbol, and the calculator is in the ready state. Then I enter a digit, doesn't matter which digit, anything from 0 to 9. The calculator will start building operand 1. Operand 1 is anything to the left of an arithmetic operation, like plus, minus, multiplication and division. If I press another digit, it simply goes into operand 1. So I go round and round and round as long as I keep pressing digits. Then when I press plus, minus, multiply by or divided by, I go into this state, the save operator state. And here the state machine saves the mathematical operator. Then when I enter a digit, I go into this state. And now I am building operand number 2. So when I keep pressing digits, I go round and round and round. I stay in this state, building operand number 2, until I press the equals symbol. And then the state machine goes into the show result state, and it will calculate the result of the calculation. So what have we seen? The state diagram shows states. Mind you, there can also be activities. Each state can be an action that the state machine performs. So a box is either a static state, like a static state that the system is in, or it is a specific activity that the state machine performs when it is in that state. The state diagram shows all allowed transitions between states. And two more. A state diagram can be nested. So a state in a state diagram can have an internal state, and you can have an internal state diagram to describe that internal state. And a state diagram can depict internal activities. Now, internal activities are, let's say, they are methods that are only applicable to that specific state. For example, let's say you have a video conferencing system and you make a connection. So you could imagine the system goes from disconnected to connected, and then when you click hang up, it goes to disconnecting, and then it's disconnected. So disconnected, connecting, connected, disconnected, disconnecting, disconnected, something like that. If I want to change the volume of an ongoing call, I could only do it in this state when there is an active connection. So this would be an internal activity. It's an activity, like an operation, a procedure to perform, but it's only possible in a specific state. In a state diagram, it would be an activity that doesn't change the state in any way. So the state machine stays in that particular state, but it performs an action on the side. So the diagram shows states or activities. It shows allowed transitions. State diagrams can be nested, and the diagram can depict internal activities. The activity diagram. Activity diagrams are used to depict procedures. If you're familiar with flowcharts, then you've covered this entire subject. Activity diagrams are the modern successor of flowcharts. So they're a way to describe a procedure or workflow. So in this example, I created a simple activity that represents a store that receives an order, and then here's a split. It's called a fork. So these two activities execute in parallel. So the order is fulfilled and the invoice is sent at the same time. And then here we make a decision. Is it a priority order? No. Then we have normal delivery. Yes, we have fast delivery. Here is a join where the different paths are combined. And here the order is set to shipped and we exit. So activity diagrams show a process or a workflow. Again, they can be nested. You can nest activity diagrams inside other diagrams. So each activity shape can have an entire new activity diagram inside it. Activity diagrams can show concurrent actions, so actions that execute in parallel. And they can have swim lanes. A swim lane is basically a specific actor executing activities within the diagram. So a swim lane would look like this, for example. So two lines depicting a lane, and this would be a specific actor which executes fill order and send invoice. And here you could have a second swim lane, and here you could have a third. So sometimes activity diagrams are structured as swim lanes. The layer diagram. The layer diagram describes areas of concern and the components and classes that live inside those areas of concern. So in my example, I have 3 layers, 1, 2, and 3. And each layer contains objects. Now layer 1 is obviously a presentation layer because it has a model, a view, and a controller. Layer 2 is a business layer because it has order, customer, and product. And layer 3 is a data layer. It has a connection, a table, and a record. So layer diagrams are not a standard part of the UML specification. They were invented by Microsoft. Layer diagrams clearly show the areas of concern, but they also show the references between the areas. Look at this. These are references. So this diagram basically tells me that a call from model to connection is not allowed because there is no direct reference between layer 1 and layer 3. And that brings me to a very nice aspect of layer diagrams. They can be validated. You can actually take existing code and validate it against a layer diagram to make sure that the references are all correct. And this is pretty awesome. Finally, the use case diagram. Use case diagrams are high-level diagrams that show the external actors interacting with your system. So in this case, a customer and a waiter. And the use cases. Place an order, serve an order, and serve wine. So in this case, obviously, we are talking about a restaurant. We have a customer ordering food and a waiter bringing the food, serving the food, and optionally serving wine. So you can see that the waiter serves and the customer orders. These lines depict the use cases connected to the actors. And here is a generalization line that says that serving wine is a special case of serving an order. So you can put generalizations in here as well. So use case diagrams show actors, they show use cases, they bind actors to use cases, and they can depict generalizations. They can derive one use case from another. So in this lecture, we looked at 7 popular UML diagrams.